Welcome to System Design course, Module 1, Principles of Combinational Logic. The course objective for Module 1 are illustrate the simplification of algebraic equations using K-map and illustrate the simplification of algebraic equations using Queen-McCluskey technique. The contents of Module 1 are definition of combinational logic, canonical forms, generation switching equations, looking at the truth tables, K-maps, simplification of Boolean expressions for 3, 4, and 5 input variables, incompletely specified functions, which we call it as don't care terms, and also simplifying the max term equations using K-map. And the last technique, what we study for Module 1 is Queen-McCluskey technique for 3 and 4 variables. And the contents of today's session, the session 1, are logic functions, definition of combinational logic, block diagram of general logic design sequence, problem statement of truth tables, deriving switching equations, multiple choice questions, and assignments related to session 1. The three basic functions what we have in Boolean algebra are not, NAND, and OR. Not is nothing but the inversion, the inversion of the input. If the input is 0, the output is 1. If the input is 1, the output will be 0. As you can see on the screen here, and not is represented by here S is equal to X bar. S and X are two binary variables. S is an output binary variable, X is an input binary variable. S is nothing but X bar. It means that the S is equal to the complement of this X here, right? And this complement is represented by a bar, or it is represented by a first of a symbol. Not is called as a complement or inverter function. The truth table is given here. If the input is 0, the output is 1. If input is 1, the output is 0. And the logical gate symbol for NOT gate is shown here. And as it says AND, it means that all the condition has to be satisfied in order for output to be at logic 1 or for output to be true here. In the sense, take an example that I want to buy a book only if that book is written by a particular author and if I have the money to buy that book. If both the conditions are satisfied, then only I'll buy that book, right? If the author has written that book and also if I have the sufficient money to buy it, then only I will buy it. It means that both the condition has to be satisfied in order for me to buy the book there. And it is represented as here S is equal to XY, or it could be also represent S is equal to X, the multiplication symbol in Y, what we have it, and this symbol specifies AND operation in Boolean algebra, and S is equal to in the bracket X, Y here. And all the three expressions are read as what? S is equal to X and Y. When both the conditions are satisfied, the output is equal to logic 1. If any one of the condition is not satisfied, the output is equal to 0. As you can see from the truth table here, when both X and Y is equal to 1, the output is equal to 1. For rest of the combination, the output is equal to 0 there. And for a 2-input AND gate, the logical symbol is shown here with X and Y as the input binary variable and S is the output binary variable. Or as it says or here, if any one of the condition is satisfied, then the output is equal to logic 1, right? And this is represented as S is equal to X plus Y. The plus symbol in Boolean algebra is used to represent OR operation, X plus Y, and it is read as what? S is equal to X or Y. If any one the condition is satisfied, the output is equal to 1. As you can see from the truth table, And both the conditions are false, the output is also false. Logic 0. If when any one of the condition is true, the output is equal to logic 1. And the logical gate symbol for a two input OR is shown here with input variables X and Y and S as an output binary variable. The two derived functions what we have is NAND and NOR. NAND is nothing but the complement of AND. NOR is nothing but the complement of OR operation. As it says here, a NAND function is defined as an AND operation followed by a NOT operation. Right? It means that since we know the truth table for an AND, take the complement of AND, you get NAND operation. Right? For AND, we know that when both the conditions are satisfied, the output is logic 1. For rest of the combination, it is 0. So that when I take the complement of that, what you get here? 1, 1, and 1. And for this one, when both X and Y are 1, the output is 0 for NAND operation. As I said here, the NAND is nothing but what? An AND operation followed by an inverter here. So that what is the logical symbol for a two input NAND here? X and Y are the input variables. And you can see here it is represented XY with a first of a symbol, or you can represent it by a bar here as it is shown here. And what is a NOR? NOR is nothing but the complement of OR. So that what is the complement of OR? You get it as 1, 0, 0 and 0 here. And how it is represented here? As I said here, it is followed by the OR gate followed by NOT operation, and it is represented with the bubble in front of it. You have a bubble in front of the OR gate. This is the logical symbol for a two input NOR. The other two derived functions are XOR and XNOR. XOR, we call it as an odd function. When odd number of inputs is equal to 1 or true, the output is equal to 1. XNOR is a thing is called as an even function. When I say even function, when you have even number of inputs which are true, then only the output is high. And XNOR is nothing but the complement of XOR operation. So that I can see the truth table for XOR here. Right? We have input variable X, Y, S is an output. Right? It says it's an odd function. When you have odd number of inputs, you can see here it is 0, 0, so that the output is 0. Next input combination is 0 and 1. Now if you have an odd input which is high, so that the output is high. Here X is 1, Y is 0. Right? Again, this input is high, so that this is equal to high. This is 1 and 1. Right? As I said, since it is an odd function, then only the output is high. For rest of the things, it is 0. Right? And the logical symbol for two input XOR gate is shown here. X and Y are the input, and Z is an output binary variable. And XOR is nothing but, as I said here, it's a complement of the XOR. So that since we have 0 here, we have 1. It is 1 here, we have 0, 1, 0, 0, 1. As I said, it's an even function. 0, 0, so that the output is 1. When both input X and Y are 1, 1, the output is equal to 1. For other combination, it is 0. And the logical symbol for a two input XNOR is shown here with X and Y as the input and Z as an output binary variable. What is a combinational logic? Combinational logic is a type of digital logic which is implemented with Boolean circuits where output is a pure function of present input only. It means that the output depends on the combination of inputs, right? And also in combinational logic, we don't have any feedback from output to the input. And these are constructed from functionally complete gate set are said to be combinational. It means that when I say combinational circuit, the output is a pure function of combination of inputs only, and there is no feedback from output to the input. As it is shown in the block diagram of a combinational logic function, we have a set X, which is which is a set of input variables x0 to xn, and we have a set y, which is an output set, which is a combination of output variables y0 to ym, right? And this combinational logic function is represented as the set y, which is an output set, is equal to function of input set. It means that the output is a pure function of input variables, the combination of inputs. And what are an example for a combinational logic circuits? Adders, subtractors, decoders, encoders, multipliers, dividers, display drivers, and keyboard encoders. Now, the next topic, what we have, generate logic design sequence. We'll understand how the logic design sequence runs. The first thing is problem statement. First thing is we have a problem statement given to us. From the problem statement, understand what is the problem and identify the number of variables, right? Identify the inputs variables and output variables and see from the problem statement how the output variable is affected depending on the input. Once you have an understanding from the problem statement, you can come with a truth table having a number of input variables and output variables for that. Once you have the truth table constructed for the given problem statement, come with a switching equation and simplify that Boolean expression. You need to the simplification of Boolean expression is required because the logic function still remains the same, but the number of gates to implement the given logic is reduced there, right? Once you have the simplified Boolean expression, come with a logic diagram and build the logic circuit. And the logic circuits could be built using different logic families. We have TTL logic family, which stands for transistor logic. The other logic family is ECL, emitter coupled logic. And the third one, the most what we use is CMOS, which stands for complementary metal oxide silicon, right? Using these logic families, we can implement the logic. And this is how the design sequence is done from problem statement to till the logic is built. Now we'll see how to come with a truth table from the given problem statement. The first example we will look here. I think this is you can see from the diagram here. We have a conveyor belt here. I think if you have gone to the airport, you can see that the luggage, all the luggages are thrown on the conveyor belt here, and we stand to collect our luggage. Right? We have a conveyor belt here, and for this conveyor belt to move, right? In order for this the luggage to move, right? The motor for this conveyor has to be started. And what are the conditions for this electric motor to start? And what are the conditions which is given here? The first condition, what it says is that if the material which needs to be moved is present. The first thing is for the electric motor or the conveyor to start, the material needs to be there on the conveyor belt there. That is the first requirement. Second, the protective interlock switch is closed. That protection switch, whatever is there, that needs to be closed. That is very essential. And what is the third condition? At least one of the operator is at their position. As you can see in the diagram, we have two operators, operator 1 and operator 2, A and B here, right? It means that at least one of the operator, whether it is either operator 1 or operator 2 or both, right? Right? When these three conditions are on, then only the electric motor for the conveyor has to be started. When the motor is started, then only the material whichever you place on the belt will move forward. These are the conditions what we have. Right? Everyone understood the problem statement here? Here, what are the condition we have? The condition is the electric motor, when to on the electric motor, right? When to on it, off. When to on, what are the conditions for owning the electric motor? The material needs to be present, and one of the operators, what we have, operator 1 or 2 needs to be present, and also the protective lock switch what we have for the conveyor, that needs to be closed. If these conditions satisfied, then only the electric motor needs to be turned on, right? Now you understood the problem statement. Now for this given problem statement, come with a truth table. In order to come with a truth table, the first thing is you need to identify the variables here, input and output variables. We know that the first thing is, we can say that what is an output variable here? It is electric motor. This is a parameter which is dependent on all these three conditions which is written here, right? So that the output variable, one output variable is electric motor, turn on or off. And the other input variables are, the first one is material, that is one input variable. The switch is one input variable, and at least one of the operator is that. It means that we have third input variable and we have the fourth input variable, right? Everyone understood the problem statement, and from the problem statement come with a variables, input and output variables. So that the first thing what you do is identifying the variables and see which are input variables and which are output variables. So that I've shown here, A and B are the binary variables or operator 1 and 2. M is our signal to turn the motor on and off. This is our output variable. S is the interlock switch, and M is the material present. Right, now we have input and output variables. Now you can write the truth table for the given problem statement. Now this is the problem statement. The truth table written for the given problem statement. What we have: A, B, M, and S. And this is the signal to turn the electric motor on or off. How do you do it? When the motor will be on? When? But this is M is nothing but the material. The first is the material has to be there. The interlock switch has to be on, right? So that what we have a material here, right? You can see here the material is there, and also the interlock switch what we have, right? Interlock switch is also high. But what about the operator? There is no operator. Operator 1 is also not there. The operator 2 is also not there. So that the electric motor is still not turned on here, because that either of these condition has to be satisfied. So that where you can see that either of the condition here, you can see here, right? The material is present, the interlock switch is closed, and also one of the operator 2 is present. When all these three conditions are satisfied, turn on the motor for the conveyor here. You can see from this one, right? Turn on, right? Similarly, what of the other condition we have it here? You can see from this one, right? The material is present, the clock, the switch is closed, and the operator 1 is present. Turn on the motor. And also we have for the last condition here, right? All the operator present, material is present, and the lock is also closed. So that turn on the motor here, right? We'll go to the next problem. Everyone understood how, for the given problem statement, how to come with a truth table. We'll look at the second example here. And what is the problem statement given here? Design a combinational logic truth table so that an output is generated indicating when a majority of 4 inputs is true here. Right here, as part of the problem statement, it is already given that there are 4 inputs, so that we should have 4 input variables, right? And how the output will be affected Depending on the input here, it says when majority of the 4 inputs is true. What is the majority out of 4 here? It is 3 or more than 3. That we call it as a majority, right? When 3 or more than 3 inputs are high, then only the output is equal to high there, right? This is the combination, the problem statement what we have. So that what are the input and output variables for this one? As it says, there are 4 input variables. I will take the 4 input variables as I1, I2, I3 and I4. And there is one output variable. I take it as O1. Now construct the truth table for this one. 4 inputs, output is equal to 1. And how the output will be? When the output will be high? When majority of the inputs are high. Since there are 4 inputs, what is the majority here? 3 or more than 3, right? Then only the output is equal to high. You can see from this one what we have here. When 3 inputs are high, the output is equal to high. Similarly, the last 3 combinations we have, the output is equal to high. For rest of the input combination, the output is equal to 0. Right? Everyone understood this one? We'll go to the next problem. Now again we have in this third example, we have a conveyor belt and the materials, we get it from 3 sides. We have here the first side, right? The materials come from here, the materials come from here, and the materials come from here, right? If the material is there on any one of this conveyor belt, this electric motor needs to be turned on, right? So that, and the one of the conditions what we have is the first thing, as I said here, right? If there is material on any one of this, S1, S2, and S3, right? This conveyor belt, the electric motor needs to be on if any one of the materials is there here. And also one more condition what we have, if there is any material on this conveyor belt, if I call this as a source 1 here, right? If you can see here I've written it as S1 and M1. S1 is nothing but the sensors. S stands for the sensor, M is the motor. We have 3 motors, M1, M2, M3. 3 sensor, S1, S2 and S3. And we have one more motor which is M4 here, right? If there is a material on any one of these 3 conveyor belts here, this motor needs to be turned on. And one more condition for this one is, if there is a material on this source, if we call this as a source 1, right? Source conveyor 1 belt, right? If there is any material, the electric motors for which is on the motors what we have here for these 2 conveyor belts, 2 and 3. The motor 2 and 3, these 2 motor needs to be turned off, right? So that whatever material we have, since there is one material here, this M4 has to be on, right? Hope everyone understood the problem statement here. The problem, the condition here is, for this motor M4 to be turned on, there has to be material on either of this. If there is a material on either of this conveyor belt, the motor has to be turned on. Also, if there is any material on this source conveyor belt here, the motors M2 and M3 needs to be turned off, right? In the sense, if you can just by looking at this one, what we have is all the motor turn on and off are the output variables, and the sensors are nothing but the input variable, and the sensors will say whether the material is present on the belt or not, right? If everyone understood the problem statement, so that by just looking at the problem statement and the diagram, we know that there are 4 input variables which are nothing but the sensors S1, S2 and S3, right? The 3 input variables and 4 outputs, M1, M2, M3 and M4, whether to turn on these motors on or off, right? So that how do you do this one? We have S3, S2, S1, the three inputs what we have it, the sensor information, and the four outputs M1, M2, M3, and M4. These are the motors, electric motors. Now here you can see here for S1. Now we have a material. Now we have a material on the first conveyor. Since it is one here, right? And the respective motor has to be turned on. Which is the respective motor we have it? M1 has to be turned on here. And since there is a material on S1, what I said here, the M2 and M3 motor needs to be turned off here. But as you can see from this one here, the fourth one, right? You can see here, there is a material on S1 and also there is a material on S2. But since there is a material on S1, what was the condition it said? If there is any material on S1, M2 and M3 electric motor needs to be turned off. So that you can see here M3 and M4 are turned off. And since there is a material in S1, the M1 material is M1 electric motor is turned on. So that this is turned on and the M4 also needs to be turned on here, right? Now here also you can see from this one. This is one of the other conditions we have it, right? It says 110, right? We have materials on S3 and S2, but we don't have any material on. But we don't have any material on what? S1, right? Since there is material in S2 and S3, the electric motor for respective conveyor belt, which is M2 and M3, needs to be turned on. Since there are material, the M4 needs to be turned on. Now here what we have in the last condition, we have materials on the three belts now, three conveyor belts. Since we have material on S1, and what was the condition? It says if there is any material in the first source, M2 and M3 electric motor needs to be turned off, and only the electric motor M1 needs to be turned on. Since there is a one material here, the M4 needs to be turned on. Have you understood this one? Right? The three examples which I gave, in order to understand the given problem statement, at first understand the problem statement, come with the variables, input and output variables, and construct the two tables. While constructing the table, remember the condition, how the outputs is impacted because of the input. Next, what we have is deriving switching equations. Like now we came within truth table. The next, as we saw the generation of design sequence, right? The first step was problem statement. The next was coming within truth table. Once you have the truth table, derive the switching equations looking at the truth table. Now, how you do that, right? You can see from the previous slide for M1 variable, right? We can go to the M1 variable here. You can see for this one, M1. For these input combinations, for the second combination it is 1, for this combination it is 1, this combination 1, and this for this one it is 1 here, right? Now if you see this one, now what are the three input variables we have? S3, S2 and S1, right? You can see here it is S3 is 0, S2 is 0, and S1 is 1, right? In positive logic, if the variable is 1, we represent it as S1. If in positive logic, if the variable value is equal to 0, we represented that by bar. So that since S2 is 0, we represented by S2 bar. Here also the S3 is 0, right? So that we represented that by S3 bar here, right? It means that for these four input combinations, the motor M1 is 1. It means that for these input combinations, the electric motor is turned on, which is motor number 1. Right? So that how do you write it? As I said here, the combination, it was the M1 was on for 0, 0, 1 here. Okay, yeah. Now if it is, if you see this one, what you can write it, you can write it as this as a 0, right? Just please bear with the handwriting for this one. 0, 1. Now it is S3 bar. When it is bar, it is 0. This is 1 or 1. This is 1. Since S2 bar here, it is 0. It is S1, it is logic 1, 1, 1, and 1. What it says is that for these input combinations, the output variable M1 is equal to 1. For rest of the input combination, the output is equal to 0. So that how do you write the Boolean equation for this M1 variable? You can write it as for this combinations, right? The output is equal to 1. For this combination, the output is 1. Or for this combination, the output is 1. Or for this input combination, the output is equal to 1. Right? Everyone understood how to come with a switching equation looking at the truth table. Now we look at some of the multiple choice questions. The first one is the output is high only when both the inputs are 0 to gate. The gate is, it says that the output is high. High is nothing but the output is equal to logic 1. The output is equal to true only when both the inputs are 0. It means that there are two inputs, and when both the inputs are 0, the output is equal to 1. Which is that gate? As we studied, it is equal, it is NOR gate. It is NOR gate. Next, second question. De Morgan states that A or B whole bar is equal to, right? If you see this one, I've included the one choice, multiple choice question, which is on De Morgan's, one of the postulates of the Boolean algebra. What it states is that, right, the complement of A or B whole bar, right? The complement of this OR function is equal to what? It is equal to A bar dot B bar here, right? This is the one of the De Morgan's theorem, and very important theorem, right? What it says is that the complement of the sum of the input variables A and B is equal to and of the individual input variable, the complement of the individual input variables here. Right? The third question, for XNOR gate, the output is 1 if, as I said here, XNOR is nothing but an even function. When I say even function, even number of inputs is equal to 1. So that the correct answer for this third question is B. Which of these are universal gates? Which are the universal gates here? The derived functions, what we have, NOR and NAND, we call it as a universal gates. For which gate, when the two inputs A and B are equal, the output is 0 and otherwise 1. Which is this operation? This is nothing but XOR, as the statement is given here. When two inputs both are equal, right, are equal, the output is 0, otherwise 1. We saw that from the truth table of an XOR, when both the inputs are 0, 0, the output is 0. When both the inputs are 1, 1, the output was 0. For rest of the two input combinations, The output was high for XOR. So that the correct answer for this one is XOR. The sixth question, identify the correct table having three input variables A, B and C and whose output will be high only when majority of the inputs are high. Okay, this is similar to the example 3. What it says, the output will be high only when the majority of the inputs are high. Since it is 3 input, what is the majority here? It is 2 or more than 2. When 2 or more than 2 inputs are high, the output is high. See that condition in which to table it we have it. You can see here it is 1 1. It is 1. What we have here 1 and 1, it is 1 1 and 1 1 and 1, this is equal to 1, and when all the three inputs are 1, it is equal to 1, right? So that the correct table for the given problem is C here. Just look at this one. Yes, if you see here, no, it's not C here, I can see here is 0 0 1. For this also it is 1. You can see it is B answer 1 1 1 1 1 1 1 1 1 1 1 and 0. For rest of the combination it is 0 because you can see here when C is 1, right, it's not a majority here, so that it is 0. When all are 0, it is 0. And again you can see only B is high, the rest of the two are 0. It is not a majority, so that the output is 0. Again you can see here A is 1, both are 0. It's not a majority, so that the output is 0. Yeah, be very careful when you have this kind of problems. Next, which among the below are integrated circuit families? As we discussed in the session, in today's session, which are the IC families? TTL, transistor logic, emitter coupled logic, complementary metal oxide, and the fourth one it says all of the. Yes, all of are the IC logic families. The eighth question, determine the output X operation looking at the waveform. As you can see from this here, we have two input variable A and B, and X is in output. And you can see here, this line is on logic 0, and this line what we have is a logic 1. So that you can see here that A is 1, in this period A is 1, B is 0. The output is equal to, in this period, this is equal to 1. And again, if you see when both A and B are 0, the output is 0. Right? You can see here when B becomes 1 and A is 0 here, right? Again, the output is high. And you can see here in this period, B is 1 and A is 1, right? When both A and B are high, the output is equal to 0. So that now you can you relate this, the waveforms with the truth table what we studied? It is nothing but an XOR operation. If any one of the inputs is high, if it is an odd function, the output is equal to logic 1. As you can see here, A is 1, B is 0, it is high, right? If B is 1, A is 0, the output is 1. For rest of the input combination, it is 0. The ninth question, identify the name of the operation that produces a high output whenever the two inputs are at the same level. So that it is nothing but what? It is an XOR operation. It says that produces a high output when the two inputs are at the same level. You can just recollect from the truth table. When both X and Y were 0, the output was 1. When both X and Y were 1, 1, the output was, again, it was 1. For which truth table you saw that one? It is for the XNOR operation. X or X bar is equal to. This is again one of the Boolean postulate which I wanted to highlight it here. And that is the reason why I've given this as a question. X or X bar, this is equal to 1. Right? You can see here the X or 1. If X is 0, what is an X bar? It is 1. It's an OR operation. If one of the condition is satisfied, the output is equal to 1. So that the correct answer is A for 10th question. And these are the assignments. You need to draw the truth table and logic symbol for 3 input variables. I've explained for 2 input variables. Do the same for 3 input variables. Construct a truth table and also draw the logic symbol. The logic symbol still remains the same. It only the number of inputs is 3 here instead of 2 what we discussed. And also explain the block diagram, general logic design sequence. We have discussed this one, explain that, draw the diagram and explain the importance of each of those blocks. The third question, explain combinational logic with example. Define combinational logic, draw the block diagram of the combinational logic and how the output is related to the input. Write the equation y is equal to f of x. And what are the example for combinational logic? It is adders, subtractors, right? Those here. Thank you, everyone.